Shell and tube heat exchangers are one of the two most common types of industrial heat exchangers. They have a simple design, high flow, and high heat transfer rates, but they typically require more space than a plate heat exchanger. Is it possible to improve their design using additive manufacturing? Hello everyone, Yuki from nTopology, and today I will show you how to create a workflow that generates a customizable single pass, counterflow, 3D printed heat exchanger in the form factor of a traditional shell and tube heat exchanger. Let's get into it. My design goal is to create a heat exchanger with the same external dimensions as a traditional shell and tube heat exchanger while taking advantage of additive manufacturing to increase its heat transfer efficiency. I created this workflow in nTopology that generates a fully customizable heat exchanger. Let me show you how it works. Shell and tube heat exchangers commonly have a cylindrical shape with round channels on the front and rear. I generated a cylinder and placed two spheres on each side to recreate that cylindrical shape. I used the length and radius to control the form factor of this heat exchanger. Next, I added in the inlets and outlets. I can define variable specific parameters such as the radius, the length, and the position to control the size and the location of my inlets and outlets. Now once I've defined my volumes and basic shape, I can then Boolean union them together and create a shell. Now I can start working on the core of this heat exchanger. Since I'm creating a heat exchanger with two fluid domains, I will infill the design space with a gyroid TPMS structure. Gyroids provide a large surface area for heat transfer, naturally separates the flow into two domains, creates very stiff thin-walled structures, and are self-supporting and easy to print. Once my wall TPMS are in place, I can convert the main design parameters to a variable. I made the cell size a variable so I can freely control how big or small I want these cell sizes to be in the X, Y, and or Z direction. I also made the wall thickness a variable to be able to control the thickness of the wall. And lastly, I also pulled out the bias. The bias swifts the walls of the TPMS structure, which allows me to increase the flow in one domain while restricting it on the other. Now once I'm satisfied with the gyroid core and fluid paths, I can add in baffles to prevent the two fluids from mixing. I pulled out the thickness variable here to be able to control the thickness of these baffles. To wrap things up, I used a simple Boolean union to combine all of the elements of my heat exchanger. If needed, I can add a fillet where the gyroid core meets the shell to increase its structural stability. Since the shell and tube heat exchanger is going under some thermal loading and pressure, I can also add in some ribs on the outside of the shell to help keep their shape while undergoing thermal expansion. Currently, I have my rib set to triangular honeycombs, but I have the option to set it to a different unicell type as well. I do want to mention that I have created a fully parametric model in nTopology, so you can easily customize the outputs. Another way would be to import existing CAD files. You can import your basic representation of your shell and tube, and the workflow would be more or less the same. Now I know this workflow will work. I can condense this entire workflow into one single block using the variables that I pulled out earlier. If I were to open a new instance of nTop and import my reusable workflow, I could change up a couple of inputs and generate multiple iterations of this heat exchanger. And suppose I'm happy with the result of my shell and gyroid heat exchanger. In that case, I can mesh and export my mesh to run a thermal, CFD, or even a conjugate heat transfer analysis to evaluate the performance of my design. Now, why would you want to do this? Maximize heat transfer, minimize pressure drop, and minimize size. There are many benefits of additive manufactured heat exchangers over their traditional counterparts. Standard shell and tube heat exchangers have many components. They require more space and have a chance of the shell side fluid leaking into the tube side fluid or vice versa. In comparison, you can condense a multi-component assembly into one where it is less prone to failure. These performance and reliability benefits can counteract increased costs, especially for high-performance applications in aerospace, automotive, or energy production. I hope you're able to get a lot of insight of what nTop is capable of. Thank you, and I hope you learned something new today. If you want to download this nTop file, go to nTopology.com under Resources, Videos, find this video, and at the bottom, click the link to download the nTop file. If you want to learn more about nTopology, contact us and fill out this form to speak with an nTop expert. Lastly, check out our support page at support.ntopology.com and type your questions in the search bar if you have any questions. Thank you.